Hi, everyone, and welcome back to the 2016 Hack Summit. We're joined right now by Yehuda Katz, who is a member of the Ruby on Rails and Ember.js and jQuery core teams, and is also the inventor of Handlebars, which is a templating engine for JavaScript. He's also the co-author of jQuery in Action and Rails 3 in Action, and he's also the co-founder of Tilde Inc., which organizes the RailsConf conference every year. So it's really a pleasure to have you here today, Yehuda. Thanks for joining us. I know you're such a busy developer, so thank you.
Thanks. Yeah, a lot of those things, by the way, I am alumni of those things, but I have been at some point on all those core teams.
Very good. So just to get the audience to know you a little bit better here, I'd love to just kind of ask you a little bit more about your background and how you got started as a programmer. So maybe what got you into programming in the first place? What got you passionate about it, and what do you love about programming?
So I first got into programming as a kid, actually, but not the normal story. I programmed QBasic for a little while, and at some point, my uncle gave me a book that was the KNRC book and said, if you really want to be programming, do this. And I sort of read through it at 8 years old, and I was like, this is impossible. Basically, what that means is that QBasic is a toy programming language. I cannot actually program, and I sort of abandoned programming at that point for basically until my 20s. But what actually got me into programming in the first place, in the more modern era, is that I was a newspaper designer, and I got a job as a web designer, thinking that it may be related in some way to design. And the first task that I ever had was I had to make a form for people to sign up for a nonprofit dinner. And the form was this is 2005, so there was a sort of normal story where it was like, please put in your name, your address, your city, state, zip, please, all this stuff. And I felt like, why? It seems like once you have the zip code, you already know the city and state. So why do I have to type in all this information? It seems terrible. Surely there is a way for me to only require the user to type in the zip code and derive the city and state. So this was like 2004-ish, and it was hard. And was not even easy to get the database or whatever, but that wanting to make the form more ergonomic for users was what started me going down the path of, obviously that is done using client-side JavaScript, and I started going down that path. And eventually, at a training course that I was at, someone said, "Oh, by the way, if you like this stuff, you should really check out Rails." Also in the same era, so I basically just ended up getting involved in both jQuery and Rails pretty early in both of their lifetimes, because I was basically feeling unhappy with the static content. This is what it is. Here's a form. Please fill it out. View of the world. I felt like it was wasteful.
It's a great story, Yehuda. So I'm going to go ahead and let you run with your presentation. Yehuda has a presentation on frameworks, which I think is very relevant to our audience. You might remember, audience, that there's been a lot of opinions back and forth throughout this event. Bob Martin came on yesterday and recommended that we look at frameworks in kind of a jaded eye, so to speak. And Yehuda would like to express his views on frameworks. And I think you'll find it very enlightening. And audience, please feel free to ask questions in the Q&A section, and we will address those at the end of Yehuda's presentation. So Yehuda, take it away.
Okay, so yeah, you can see the title of my presentation is perhaps the opposite of the perspective that you should use. Look at frameworks with a jaded eye. But I want to start off just by saying I don't think that frameworks are the correct answer for every problem, or that basically intrinsically you should use a framework whenever you start any kind of project. I think that's obviously wrong. What I'm hoping to accomplish today is just to talk about what kinds of problems frameworks are trying to solve, and how you might think about those problems, and why frameworks really do genuinely solve a problem that's hard or impossible to solve without them. So first of all, just as a framing device, because this is something that really is an axiom of mine that drives a lot of my thinking, is the concept of cognitive depletion. The concept of cognitive depletion is basically that human beings have a certain store of available cognitive resources, and those resources are depleted with a lot of different things. So you're making a choice depletes your cognitive resources, but so does thinking hard, solving puzzles, getting into an argument. And I think you can sort of have form an intuition for this by thinking about the fact that if you wake up in the morning in a good mood and get into an argument with your friend before you get to work, by the time you get to work, you're pretty drained and may not be in the mood to do any work. Conversely, if you're in a good mood and you wake up and get to work, you may be able to dive right in and get some stuff done. But maybe if you encounter a couple of annoying choices or annoying roadblocks, And it seems like the roadblock itself may only take a minute or 5 minutes. After actually doing that work, maybe you feel a lot less ready to do more work. So that's sort of the intuition behind it. This is a pretty well-studied science, but it really forms the basis for what it is that the convention over configuration story is about, which is not exactly the same thing as frameworks, but the basic idea here is people only have a limited store of resources to think about things in. And if you make people think about things that are low value, they will end up not having the resources available to think about things that are high value. So a lot of times you'll hear people say things like, it of course can't be bad to have more choices, or it can't be bad to have more information, or as an implementer, it can't be a bad thing to have more security. And all these things are true, right? But they're usually not thinking about the effects on cognitive depletion, right? So there may be solutions that, in fact, if you make the user think about something, they'll solve the problem in front of their face. But then they may be so cognitively depleted that the next time they encounter a problem, they won't be able to. They'll think about that problem in a tragically wrong way, and fail all over the place. And we'll talk more about that as I go. So first, sort of related to this point. And so you might be thinking, well, cognitive depletion, that's like a thing about junior programmers. I'm, of course, a senior programmer. I will never have this problem. And sort of a related point, and this is something I've just observed as a programmer, is at some point, sloppy code is a reality. So you're going to have some amount of sloppy code in any code base. And that's not because people are good or bad programmers. It's not because they work hard or work not so hard. It's because at every point, whether you're a single programmer team or a big team, there comes some point where you're sufficiently cognitively depleted but still have work to do. And so, and I think everybody has experienced this, where you're at the end of a long yak shave and you just really want to ship whatever the thing is, but you hit another roadblock and you just go to Stack Overflow, grab whatever thing, paste it in, call it a day. Now, again, you might think, oh, nobody should do this. We should really be focusing on building a world where people don't do this. And I just sort of accept as physics that either when you're tired, or you hire a junior developer on your team, or it's the end of a long project. There's all kinds of reasons. You had an argument with your wife that day, right? It could be any number of reasons why even a very good programmer is cognitively depleted. It results in them writing some amount of sloppy code. So I consider it effectively physics that there's sloppy code in the system. So given that there's some amount of sloppy code in the system, you think about how you want to deal with that problem. What's the solution to that problem? And so what is the real problem that sloppy code causes? It's not a morally bad thing. It's not a bad thing in and of itself. The problem with sloppy code is that sloppy code can affect other code, right? So if you think about a small function, maybe the small function is 5 lines of code and it does really bad stuff. If that sloppy function is using lexical scope and you dealing with its parameters in a particular way, right, then that sloppy code you don't have to worry so much about. So you might look at the code and say, that's disgusting. I hate that code. It's terrible. I really wish I could refactor it. But if it's sufficiently isolated from the surrounding code, it's no big deal. And the general philosophy for dealing, I think, in programming, and this is not just frameworks or anything, for dealing with the problem of sloppy code exists, is to allow people to write some sloppy code, but try to set it up so that the sloppy code doesn't just in and of itself affect other code. And this is the problem with GoTo, right? So the problem with GoTo is not that GoTo is intrinsically bad. Maybe GoTo is okay if you write a small program. The problem is that GoTo has effects on the entire program. So if you let someone write GoTo in one place, it's hard to predict how that affects the whole program. Basically, the solution that people have come up with is varying levels of isolation, right? So functions are isolated from each other except through their parameters and their surrounding scope. Modules have an even stricter isolation primitive, and maybe like on the web, iframes have an even stricter isolation or workers, right? So we construct levels of isolation where writing sloppy code inside of one of them does not necessarily affect the outside world. So what's an example of this in my field, in the web framework field? An example of this is a component in React or Ember or Angular conceptually owns a DOM element. And what that basically means, what I mean by that is there's a bunch of state in the world. There's a shared mutable tree of DOM, right? So in principle, anybody can go around and mess around with any other DOM node. And that's basically how jQuery code works. But in component stories, the reason why the component stories are nice is because component stories allow you to say, even though there is conceptually this giant blob of shared state, which anybody can modify, we're going to break up our program so each little component is responsible for its little area of the DOM. And basically what this means is that if someone's having a bad day, you hire a bad developer, and they go in and do all kinds of crazy hacks inside of the component definition, inside of, in Ember, what we call did insert element, and what in React they call component did mount, right? If you do stuff inside of that hook, basically, it doesn't matter that you might write horrible code, because it's still isolated to the element that you're talking about. And I should point out that that's not enforced in any particular way very strongly. It's not language level enforced, but in practice, the path of least resistance, even for cognitively depleted developers, even for junior developers, is to basically work with the element that you're given. So really what this is about, in general, is that there's a tension. In order to build a program that is robust, that tolerates a certain amount of sloppiness, that also grows into a big program, a very big program, right? In order to do that, you want a certain level of isolation. You want functions that mostly don't know about each other, that are mostly parameterized. So that's one half of the story. And the other half of the story is that pretty much any program is operating on some shared mutable state. So perhaps there are some programs that are pure math, but at some point you're writing to standard out, you're using HTTP, you're writing to the DOM. So in almost any program, even though there may be a function that's operating on a little slice of the world, of course, there's always shared memory, right? So it's like operating on a slice of the world. There's always some bigger piece of thing that everybody is really working with. And it's very difficult to eliminate that. So as I said, an example of this is in an operating system memory, right? So there is in fact one giant blob of memory that is sliced and diced. And in the early days, what would happen is you basically, as a program, would work with whatever part of the memory that you wanted, and other parts might operate with other parts, but you weren't talking about a piece of memory that looked to you like the whole world. You were looking at a piece of memory that was part of a bigger world. And that is just intrinsically messy, right? So if I'm allowed to address somebody else's memory, and the rule is just please don't do that, then I can do that, and I can mess with another program. So the other program can't have any guarantees about anything. And so something that we did very early in OSs is we came up with this idea of process isolation, which is the idea that and virtual memory, which is the idea that a given process can pretend that it owns the entire universe, right? A given process gets a chunk of memory from the operating system, but that chunk of memory looks to it like it starts from 0 and goes up to however big it has. And what that means is that you don't have to worry about each process messing with each other. Each process basically gets to pretend like it has the whole universe. It gets to be as sloppy as it wants. And the worst thing that happens is you're so sloppy that your process crashes. But the guarantee of virtual memory is that you cannot be so sloppy that you mess with another process or kernel panic, right? A kernel panic basically means there's a bug. Now, one thing that's sort of interesting about this is that the naive approach for doing something like virtual memory or dealing with a DOM is just you have this big blob, you have a gigabyte of memory. Every time you create a new process, just take another 100 megabytes and give it to the process. And the problem with that, and that approach actually works okay, but the problem with that approach is that each process doesn't know a lot about the other processes. So it doesn't know, I have 100 megabytes. It doesn't know whether maybe there's some 150 megabytes in another process lying around that it could in theory use. And it is actually quite important that it not try to guess that, right? So if let's say I'm Chrome and you're Firefox, and the system, we just naively sliced up the memory, and I have 500 megabytes and Firefox has 500 megabytes. It's actually pretty important that Chrome doesn't know that there's 500 megabytes sitting around in Firefox. It shouldn't be poking around trying to figure that out. And additionally, it should not be trying to coordinate with another process. Hey, Firefox, do you have any extra memory? Please give it to me. Obviously, that's not going to work. So there's this tension here, which is that if you just say, the problem is we have a shared resource that we would like to isolate from each other, you want to slice it up, you end up with a certain amount of waste. Shared memory has an obvious example of this, right? You end up with a certain amount of waste. Another example, a more concrete example of this problem is sockets, right? So let's say I am Chrome and you're Firefox, and I open up a socket and you open up a socket. So obviously those sockets are separate from each other, but at some point, when we're each waiting for new data, somebody has to take the incoming data and put it in a buffer somewhere until it actually goes into the program, right? So I'll say, hey, please read 100 bytes from this remote website or some number of K. And until I actually read the memory, it has to the data has to go somewhere. So the naive solution might be, no problem. I will create a local buffer of a megabyte. I will read into it, and as soon as the memory becomes as soon as the socket becomes available, it will read it into that buffer, and I'll get it whenever I have a chance. But the problem now is that, let's say there's 100 processes on the system that all have open sockets. They are all going to need to construct these buffers per process for any outstanding connection. And what that means is that in practice, there's going to be a ton of buffers lying around that are not doing any work, that are empty. And so the alternative solution, and the one that we ended up arriving at in operating systems, is there is a thing called the kernel. You don't actually make a connection to a remote server yourself. You don't actually get to talk about the raw mechanics of TCP. What you do is you ask the kernel, you say, hey, kernel, I would like to make a remote connection to this other location. Please let me know when there's any data. And instead of you managing the buffer yourself, the kernel manages the buffer. But and remember, you as a process don't know about all the other processes that exist in the system. You only know about yourself. But the kernel actually does know about all the processes. So the kernel can allocate an amount of space that it needs to deal with all the processes. So maybe if everybody's waiting for a megabyte of data, maybe it only has 2 megabytes of buffer lying around, and maybe it has however much size it needs, but it can basically share the memory in a way that would be very dangerous to allow processes to do, right? So the kernel is effectively operating in this little unsafe zone where it gets to deal with the shared memory in a shared way, and the individual processes get to pretend like they have their own isolated view of the world. So what is that story? What's happening here, right? What's happening here is we really would like an isolated view of the world where each process got to imagine that it was making a TCP request and that it got back the data when it was ready. But if we do that naively, we're going to end up allocating a lot of memory because the processes are not allowed to know about what other processes are doing. So what we do is we create a little abstraction here that says, instead of saying, please fill this buffer with data, you say, hey, kernel, please give me the data when it's ready. And the kernel is allowed to make use of global knowledge that it has about the whole system that would basically break individual isolated parts. And this story is pretty universal, actually. This story is pretty universal. It's the fundamental tension of why scale is hard, why scaling programs is hard. And it's, in fact, the fundamental solution to the problem of scale, right? So just to repeat the general concept, the problem of scale is that in order to make sure that you can have as effectively as many little units as you want that work together, you need to make sure that they are reasonably isolated from each other and can pretend that they are seeing their own view of the world. But in practice, they are always talking about some shared structure or some shared piece of state, like the DOM or memory or I/O. And if we just let each individual unit control the thing separately, you're going to end up with a lot of duplicated work, shared work, et cetera. So what we would like to do is we would like to have a separation where the kernel is allowed to manage things globally and the user space gets to pretend things are isolated. Okay, so method calls in a programming language are another sort of similar story, right? So a method call has a very strict isolation contract. It has its function, and the function takes some parameters, and all it is allowed to see is that those parameters are passed in. It doesn't have any knowledge of the caller, right? So the caller is, from the perspective of the method, totally separated. But in practice, it may turn out to be the case that for a given caller, let's say you have a function that says add A and B, and it says return A plus B. And now imagine that someone calls that function with add 1, 1, right? So for a given caller, and of course, from the perspective of the caller side, add 1, 1, that guy is not supposed to know what the implementation of the function is, right? This is an important isolation boundary. But but in fact, if you look at it, what you can see, well, if I actually know that the inputs are 1 and 1, I can do something smarter, right? So there is some, but you can't let either the caller or the callee do that. And so the solution here is sort of similar to the socket story, right? There's a compiler or a JIT, and the JIT or the compiler is allowed to cheat. It's allowed to break the isolation boundary. It's allowed to look at both sides and see, I see that the caller has 1 and 1, and the callee is saying A plus B. I know that that's the case, and so I can combine the story into something that does the right thing. So again, from the perspective of the caller and the callee, everything is still perfectly isolated. The caller doesn't know what the callee is doing. The callee doesn't know what the caller is. But now we have an extra little layer on top that is able to take advantage of global knowledge that the individual isolated units are not allowed to know. And as I alluded to before, this is sort of the same story about web frameworks, right? So web frameworks, you have a single component. The single component is dealing with a particular DOM node, or you have a single part of your system that's making a network request. And you may have 5 components that are all making separate network requests. Perhaps you would like to be able to say, if I'm making 5 network requests for the same thing, don't actually make 5 network requests. Please coalesce them into one, right? But you don't want to allow each individual piece to know about each other. So there are just these things that are scarce resources, but we want the isolation model to be that each unit only knows about the stuff that it knows about, so that when we put together a large amount of them, they continue to work. So that's the philosophy. Let me give a concrete example. In the browser, there is actually, or in web frameworks, there's basically one trick that makes web frameworks reasonably efficient in a plausible way. And the trick is batching work that happens during a user callback until afterwards, in case there is extra work that is done. In today's world, Ember, Angular, and React all have versions of this strategy, which I'll talk about in a second, the concrete details. Backbone did not have this strategy, and what that led to in practice was a render function could get called multiple times in response to one user callback, and that was pretty difficult, and people had to sort of manually try to deal with it. So what do I mean by that exactly? So here, let me give a simple example. I have a component here, and it has a method called click on it. And what the click method does is it sets the counter to 1 more than what it was before. I have a template, and obviously, the idea is when I click on the div, the counter will keep incrementing 1, 2, 3, 4, etc. So what is exactly happening when I render this component? And I'm going to give sort of a hand-waving answer that is sort of analogous across all frameworks. So what happens is once I click on the div, that code gets run, this.set counter to ++ this.counter. And in all existing, in Angular, Ember, and React, in all 3 of them, what happens is right now we don't actually do anything. All we do is remember that there is something has happened. We need to come back to it later. And later on, what's going to happen is we're gonna have to try to figure out what actually needs to be updated. And in all the systems, what effectively happens is that what we do is we notice, this, here's a tree of nodes. This is a tree of nodes, and 1 bit at the edge, the thing that represents this counter, has changed. And what we want to do is we're going to want to update it. Now, what might happen is there might be another. So, like I said, if you click on this div, it updates the counter. That's the little red box circle on the bottom left. But you might actually update some unrelated part during the same click for some reason. As these programs get bigger, there are more things that get handled. And in practice, there are usually many areas that get updated. So, if you're adding an item to an array, maybe you have to add an item to a list. But separately, you want to say there are 7 items instead of 6. Right? So there may be several areas that update. And basically what happens is each one of these changes conceptually makes an area of the DOM dirty, and we allow that process to continue until the user's code has finished. And then later on, at some future point, what we will do is we will start walking the tree. The exact mechanics of this are different per framework, but effectively you walk the tree, you say, this nothing to do here, nothing to do here. That thing is dirty. Okay, please update it. This thing is dirty. Please update it. This thing is not dirty. Okay, nothing to see here. Now we're back into a good state. So the important point here is that when I click on something and do an update, there may be multiple things that affects, that updates the DOM. And each individual unit, the thing that's on the screen here, the code snippet, this unit doesn't actually know about the whole DOM. It doesn't know about batching. It doesn't know about walking the DOM tree from top to bottom to look for dirty things. It just knows that it is making itself dirty. It knows that I myself am dirty. And what that basically means is that my component is allowed to think about itself as being a relatively isolated thing. I own this component. I know basically when it becomes clean and when it becomes dirty. But there's a system of effectively a kernel like the OS model that says, okay, I'm going to let you guys think of yourself as isolated, but we're not going to actually let you touch the DOM, right? You're not going to update the DOM. You're just going to let me know that there might be some work to do, and then we're going to update the DOM for you. Now, what is an example where this becomes really important? So an example where this becomes really important is sometimes you actually have some area of the tree that represents a conditional. So you say something like, if the user is an admin, then, and you have a big blob of stuff inside of it, /if, right? Or whatever equivalent thing in your framework. And if the user becomes not an admin at the same time as some contents inside of it change, what you would really like to do is, as soon as you walk top down, as soon as you discover that the user is no longer an admin, you abort dealing with anything inside of it. And in order to do that, again, you need to separate out if the conditional knows something about itself, the components inside of it know something about themselves, and there's an algorithm that walks the tree that figures out what has to be updated. Interestingly, in Ember, the tree is sort of an internal implementation detail. In React, the tree is literally the thing that you are building as a user, right? You're building a tree, and then the React algorithm is comparing the two trees, and the way it discovers that something is dirty is that there's a difference between the two trees. In Ember, we have one stable tree, and we discover dirtiness by checking the values. But conceptually, it's the same story, right? The individual components don't really understand that they're inside of a tree in either model, or at least the normal programming models, they don't think about that. But their tree walk is something that is done by the quote-unquote kernel. An example, this is actually something that comes up in the browser itself. So I just described something that frameworks do, but a similar story happens with the browser. So when let's say you say, I want to update this attribute to go from, it's an attribute called title. I would like to update it to go from hello to goodbye. Now, there may well be some CSS inside of the, in the CSS rule somewhere that cares about that. But ideally, you do not want to immediately go and read through all the CSS rules and update things. What you would like to do is wait for maybe other things to happen. Maybe people add some classes, remove other attributes. Maybe, there could be any number of DOM mutations that happen. And when all of the DOM mutations that might be happening are done, then you go and say, okay, now let me check the DOM. I see that you have changed this attribute. I see you have changed this class. And then you can make the change optimally. And this is, in fact, what browsers already do, right? Browsers do not usually, in response to you changing an attribute or a class, they do not usually immediately recompute all the value of all the styles. Interestingly, the CSS triggers thing, which you perhaps have heard of, is a exception to this rule, which is sometimes there are certain things that you do that, for some reason, force the browser to immediately flush either layout or paint or composite. And that's actually a pretty big hole in the model, right? So what you're supposed to be allowed to say is, I'm allowed to update this attribute, and I don't have to think about the exact timing of when it gets flushed. I'm basically just saying that when the CSS rule is basically saying whenever this attribute is X, make the width is 50%. Whenever the attribute is Y, the width is 100%, and you're not supposed to think about the exact timing. It's supposed to be declarative, just like templates in Ember or React. But in practice, for various reasons, the browser cannot do this reliably. So if you hit any of these triggers, and there's a big list of them, what ends up happening is that the browser is forced to abort the batching strategy and immediately flush. So you may have like 20 flushes in a single response to a user action when you could have gotten away with one, and that can be quite expensive. And that's why this website exists, to alert you to the fact that this problem exists. So what are the benefits of the walking optimization? The benefits are we can guarantee that a particular render happens only once per user interaction, right? So if the user clicks on something, I can guarantee that the work necessary to update that only happens one time. This is true about Angular, Ember, and React, but it is not true about Backbone, right? In Backbone, you don't have that guarantee. If something, now, like I said before, if something above you was removed, so if there's a if condition that becomes false, then we know that we don't even have to look at anything that's inside of it, because we, instead of allowing the update to happen in direct response to the user interaction, what happens is we wait to see if we need it at all. We let any amount of other work to happen, and if we discover that a whole region of DOM is cleared, we can ignore all that work inside of it. And there's something that I only alluded to, which is that because of the fact that you are not yourself responsible for updating the DOM, the framework is, the lifecycle hooks that you get, and React and Ember have pretty similar ones here. Angular has fewer of them. You basically have a good sense of what the state of the world is at each lifecycle point, because you know that you are not the one updating things Ember is. And of course, in both Ember and React, if you need to go update the DOM, there's still ways to do it, but you do it in a particular lifecycle hook. And that means that outside of that lifecycle hook, you have a pretty good sense of what is allowed to be the state of the world. Other things that you get from from setting up the world in a very isolated way with a global optimizer, basically, is so what about booting and initialization, right? So booting and initialization is a part of the process that's usually pretty different from the process of actually running. So there's usually some top level thing that you have to do to get your app into a running state. And then after it's in the running state, you go through the process that I talked about. But if the whole world is set up in a way that is managed by a kernel, effectively something that is responsible for rendering, then it's pretty easy to say, well, the way that this works is, the kernel knows when things are being added to the page, and it knows when things are being added and things are being removed, and that also allows it to provide some hooks for add-ons, right? So an add-on might want to say, please let me know whenever something was added to the DOM, I want to do something, right? These things are only possible if you're going through some setup. Going through some kernel. And a sort of similar story is true about like DOM mutation observers in the browser, right? If let's say you were for some reason allowed to manipulate the DOM directly, the raw data structure, it would be impossible to ask the browser, please let me know when someone mutates this DOM node. But because of the fact that you're going through the quote unquote kernel, which is the browser C++ implementation of the DOM, it's able to add more hooks that people can use. This also allows you to layer on stuff, and this is something that Ember does for you, and React Router adds on top, for example. We can add additional automatic work that happens during navigation, setup, and teardown, right? So if I navigate from one page to another inside of my Ember or React or Angular app, I probably want there to be a canonical way of tearing down content. That's probably pretty similar to if an if statement becomes false. And if we already have something that is managing the process of revalidating, walking from the top down and making whatever changes need to be made, then navigation, setup, and teardown are sort of naturally fall out of that. You also, similarly for network, if instead of making $.get JSON calls manually or $.ajax calls manually, if you're going through some kind of abstraction, that abstraction could say, oh, I've noticed that you have made 5 requests for the same ID, or you have made 5 requests for different IDs, but I know how to coalesce them. And so that separate little abstraction is allowed to take all those things and coalesce them. And really the TLDR of all of this is saying, these are all things where you would really like it to be the case that the normal way that someone writes code is isolated. You're in a function, you're in a component, you're in the code that works with a particular data model. You would really like that code to be able to not think a lot about the global state of the world because that's very brittle. But if you don't allow them to think about the global state of the world and just do the naive approach, you will end up with a lot of duplication. So this is sort of a attempt to square the circle. You make the primary worldview isolation, methods, functions, etc., and you try to add an optimization layer on top that is able to avoid the duplicated work without changing the semantics of the isolation. Now, what this fundamentally means at the end of the day is that you are giving up control to a runtime, right? So people don't like giving up control. They like to maintain control. And this is something people often say about frameworks. I am giving up control. I really would like to have control. But the benefit that you get from giving up control is that the thing that you're giving up control to is allowed to do optimizations in ways that you yourself have no knowledge of, right? So of course, it's always possible to solve this problem by just giving each component direct access to each other and making the normal programming model that components just talk to each other, or instead of passing parameters to a function, just always use global variables, and that's how you communicate, right? You, of course, can do that, but I think everyone can observe that if you do that, the world falls apart quickly. You can't write big programs, right? So the isolation, I think, is really quite important, but if we just leave it at that, if we just say isolation is important and don't realize that there is some sense of shared mutable state, there's some shared state that we're actually operating on that should be managed, then we end up with pretty inefficient programs. So the objection that you're giving up the control to a runtime is true, but it basically allows you to get a large amount of isolation and composition while still getting optimization for the few areas that are touching shared memory, or shared state. And this is basically the story. So this is not really a framework story. This is the story of JITs and kernels, right? So as I said before, JITs are allowing you to have very, very isolated programs, modules, packages, functions, right? Very good isolation story. But the JIT is able to cheat. The JIT is able to say, I know better. The isolation story means that you're not allowed to know who you're calling, but I actually do. So I can do something better here. And a JIT programmer once told me the rule of JITs is you can do whatever you want as long as you don't get caught. Right? So that's basically the story. It allows you to layer on optimizations that don't change the semantics. And kernels are sort of the same way, right? So the Linux kernel has a bunch of operations on it. And effectively, all those operations are allowing you to say, I would like you to do X. I don't want to tell you. I would like you to open a socket. I'd like you to read memory. Give me some thing from a file or whatever. And you're doing it in a way that doesn't exactly say how it should happen, but it allows a system that knows about all the resources to do something smart, all the resources and all the processes. So what this basically means is that kernels are managing the thing that is shared across all the isolation units, right? So we have these isolation units in an operating system. We're talking about processes, and kernels are working with the shared state, the global shared state, all of the memory, all of the files, right? The whole operating system. In modern Linux, all containers, right? And the important thing here is that kernels are allowed to put that mutable state into an inconsistent state, as long as by the time it actually talks to a process, it has gotten the world back into a consistent state, or it doesn't reveal the inconsistency. And what you can figure out if you have written programs that have to deal with efficiency a lot is that you actually do have to do things that are sort of integrity violating at some point, in order to avoid, for example, locking everything. You might know that you could get away with a certain amount of non-atomicity because you know that you're not going to actually expose the current state to a process until you have finished what you're doing. But of course, that's very careful and hard work, and you would not want individual processes to be able to do it. And that's sort of how the kernel works, right? So the kernel is working with all the memory, and it's allowed to put the memory in whatever state it wants. But by the time it actually gives any memory to a process, it has to get everything back into a consistent state. And processes are effectively, as far as they're concerned, they own the whole operating system, and they can't see any inconsistent state that could have happened. And the sort of the slogan I use for this is sloppy in the small and rigorous in the large. And basically, what that means is if we accept sloppy as the law of physics, people write sloppy code no matter what. What you would like to do is you would like to say, you can write whatever sloppy code you want. You're doing it inside of an isolation unit like a process or an iframe or a component. And that sloppy code, because of the way the model works, cannot leak out into the rest of the program. And I think that ends up working pretty well. Sloppy in the small, basically your job. You can write whatever you want. You can use whatever loops. You can write loops. You can use mutable state. You can do whatever you want inside of your function. But then by the time somebody's actually calling the function, they don't see any of that internal detail, right? So sloppy in the small, basically your job. You write whatever code. You're allowed to do whatever you want in the small, and the framework is giving you a framework for isolating those sloppy units from each other, and so that you know that they can't mess with each other. And something that perhaps you can intuit, and at least I do as a programmer, is that you often realize, like, if you start with a blank slate, you say, I'm not going to use any libraries or any frameworks. I'm just going to write code blank. You can realize for a little while, until you get to a few hundred lines of code, everything feels great. You're like, I don't have any of the burden of abstractions. I don't have any of the burden of these rigorous systems. I can just write whatever I want, and you are able to keep it in your head, right? So I think everyone can intuit that up until a certain level of scale, the sloppiness is pretty nice in the sense that it allows you to get the job done. And up until a certain level of scale, it doesn't have significant negative effects. The negative effects come at scale. And so the idea of sloppy in the small, rigorous in the large is we basically let you get the benefits of the small, of the sloppiness, the free nature of it, by telling you, here are the isolation boundaries. You must not cross them. If you don't cross them, you basically get to do whatever you want, and then we will make sure that the scale works. Now, one thing that's that's all true. I think you observe that this is true about programming languages. It's true about operating systems. It's true about frameworks. But one thing that's sort of hard to see is that in version 1 of something, there's a pretty rough trade-off that you have to make, because everything I just said assumes a sort of magic pixie dust view of the world where you already know all the things that you're trying to do. I know that I have to read from a socket. I know I have to read from a file system. I know I need to allocate memory. I know I'm dealing with DOM nodes, right? But of course, in practice, when you first start building some system for dealing with things, you don't exactly know what all the things that you want to do are, right? So if you say, oh, no problem, I will build isolation units for you. Here is the thing called a component, and here are the things that you're allowed to express. You cannot touch the DOM directly, or you can only touch it in these very structured ways. And I will basically make sure that the components are isolated from each other. You can say that, but because you don't exactly know all the things that people are doing yet, what happens in practice is that people feel restricted. And this is also true about operating systems, right? Like the first version of Linux, yes, you could read it. You can say, please, at a high level, read from the file, and it would try to do some stuff for you. But in practice, a lot of people ended up using direct mode, which basically bypasses the kernel's caching, the kernel's memory management, all that stuff, because they basically knew at V1, the kernel was just getting it wrong. The kernel was getting the details wrong, and it felt bad, right? So the version 1 of tools that try to do the isolate, like give you a good isolation boundary, usually end up feeling pretty terrible. And version 2 is doesn't always come. What I mean by version 2 is something specific. So I mean not exactly the second version. So Python 2 is not a version 2 because Python 2 basically continued along the lines of the original implementation. Ruby 1.8 was a continued implementation of the previous version, etc. What I mean is you get to a certain point where you say, okay, I've learned all the things I can learn at this point. I actually want to re-implement the internal architecture to take advantage of the things that I know. And so I would say that the V8 was an example of this, and Ruby 1.9 was an example of this with Yarv. Python 3 was an example of this, where you basically want to rejigger things quite considerably. And sort of interestingly, because version 2 takes a somewhat long time to arrive at, you can be working on version 1 for a long time. It's very tempting in the version 1 days to basically give up on the dream of enumerating the set of things that people want to do so that you know all the things and you can do optimizations, because you're basically not there yet. So it's very tempting to give up on the dream of that. But giving up on the dream basically means that when you go to build the new system, right? And I'll give you an example of that is Python has this feature called underscore get frame, and it basically gives you a representation of the current frame off of the current frame. So internally, there's a call stack of frames, and you can say, hey, please give me a frame. And being able to say, please give me a frame, basically implies that there is a physical representation of that thing in the implementation somewhere, which eliminates the ability to do many optimizations that people want to do in JITs. Right? So this was perhaps a nice thing to expose at some point, but it basically, it makes it very difficult to compatibly upgrade the internal machinery. In contrast, Ruby never exposed a frame object. It did expose an array of strings that tell you your call stack, but that in principle needs to exist anyway for exceptions. It might be very expensive to generate, but that is a more reasonable thing to expose. And I think at the time Ruby was more careful about what it was exposing. Another similar example is Python used ref counting for its garbage collector. So all of the C extensions in Python use ref counting. If they want to upgrade their garbage collector to something else, all C extensions will break. There may be ways to do it compatibly, but it's very tricky. Ruby early on chose conservative garbage collecting, which is not as efficient in V1, like in the early stages. But conservative garbage collecting meant that no Ruby C extension had to care about garbage collection, which meant that there have now been many updates. And it's now a generational garbage collector with incremental lazy mark and sweep and all this stuff. It has write barriers. And that stuff was possible because early on, they held the line on exposing something that would have perhaps given you more efficiency in the per isolation unit at the cost of the ability to do global optimizations. So I think that unfortunately what this means is that in V1, there is this very painful tension between holding on to the dream of the glorious future and real pain now. So one way you can address this is, like I said before, the Linux direct mode approach, where you say, I really would like you to use the optimized version or the optimizable version. I really would like you to say, please read from the file and let me figure out how to do it. But if you really need to, if you discover that there's a problem and we're getting it wrong, here's an escape valve. And FYI, if you use that escape valve, it might be fast now, but it will be slow tomorrow, but we'll keep it working. The nice thing, and an example of an escape valve in Ember and React is the did insert element or component did mount hook, which basically says, I understand that ideally you would not use jQuery here, but I realize that some jQuery exists in the world, and at least keep it contained. If you're going to drink, do it under my roof, right? At least keep it contained. One of the really nice things about escape valves, so you might want to hold the line and say, there are no escape valves. You have to do it my way. I'm holding on to the dream of the glorious future. If you do that and don't give escape valves, basically people fail. But if you do give escape valves, people can figure out, you can look at it and say, let me look at what real apps are actually doing in did insert element. And this allows you to upgrade, you can upgrade the kernel with more smarts, right? So direct mode again, which allows you to directly access the disk. Linux can go say, why are people actually using direct mode? Is that because our caching heuristics are wrong? It seems like, we're over aggressively caching in certain scenarios. Maybe we can make the kernel cache smarter so that it doesn't actually have that problem. But the only way to find that out is to give people escape valves. So escape valves are crucially important if you are trying to build something that's holding on to the dream. Basically, fundamentally, the version 1 of these systems are intentionally sloppy. They sort of get a big list of things that you could guess might be needed. TCP exists. Reading from disks exists, UDP exists, allocating memory is a thing, right? So you might provide some of these APIs, but you just don't know what you don't know. So V1 sort of intentionally has a list of things that you can keep working over time, but it's not exhaustive. And again, as I've been saying, the version 1 of systems that are trying to eventually be optimizable, systems that are quite declarative, V1 is pretty painful because your friend out there is using something that doesn't try to go through an abstraction layer, and he's able to just go read directly from the disk. So if you're writing a process and you're reading, the way to think about this, right, is if I'm a process and I do read from the disk and I have to go through an abstraction layer and you don't, but the kernel actually doesn't do any of the optimizations. In practice, what that means is that my program is slower for literally no reason. And my friend over there is able to write a fast program. And a lot of times that actually matters, right? A lot of times, you're writing Photoshop, so it actually matters that you're writing Postgres, right? It actually matters that you get the right performance characteristics. So for this reason, version 1, if you eventually want to get to optimizations, you sort of have to hang on to things that are fundamentally painful. You have to say, I know that it would be better for you to go in and write this as jQuery, but I need to insist that you follow some rules, because if you go and write something as jQuery, later on I know that that's going to be an isolation buster, and I'm not going to be able to do some optimization. So I need to insist that you do it. Again, you need to do a certain amount of escape files, but there's some limits where you have to insist that people follow some rules. Here's another example. So signals in Unix. So very, very early on, signals in Unix were basically a thing you could send to a process. So you'd say, please, hey, process, kill yourself. Please hang up. Please abort, whatever. And signals were only sent to a process. And I think in practice, this did not turn out to be the correct model. It turned out to be the incorrect model. And over time, they were like, oh, we have just added threads. Seems bad. We need to add more support. It seems like it would be nice to know what caused the signal. What is the information? If it's a sig child, which process actually sig childed, right? So there's additional information you would like to add. So you can go do that. You also eventually might want to say, hey, I realize that it seems good to wait for a signal, or it's good to know that a signal has happened, but it would also be nice if I could wait for it and say, please come back to me if 300 milliseconds have passed or whatever. And then finally, eventually you realize, oh, it would also be nice if I could say, I have 5 files that I'm waiting for, or 5 sockets that I'm waiting for. I also want to wait for a signal at the same time. So these are all features that got added. And you can imagine that at every step along the way, you said, well, we screwed up. Waiting for a signal on a process is basically hosed. We're just going to have to restart the universe. Sorry, guys, like Linux 2.0 breaks compatibility with signals. All programs are broken, but it's worth it because we realize that the universe has changed. We need to do these things. But that's not really what happens, right? What kernels do is they make their best guess for V1. And then if they discover that there's more information, they leave around what happened, what V1 was doing. They add more features, either with a new API or by being clever with compatibility hacks. And then existing programs run, and the existing programs, they continue to run, but perhaps are not able to take advantage of the optimizations. So one thing to keep in mind here, and this is something I think people perhaps get confused about, so people say things like, it is very, very important that because the web is moving so fast, or because the operating system world is moving fast, we have to break things pretty regularly in order to keep up with the times. But in fact, the web is compatible. So the web is changing fast is not really saying that the web has changed its compatibility rules. It's saying there are new capabilities, the idioms have changed, and things like that. And just because an idiom has changed doesn't mean that you have to actually remove support for the old idiom. I think for some reason people lose track of this, right? So an idiom may some idiom may become bad practice, and you might not want people to do it, but that doesn't force you to break compatibility with that idiom. You might not even be able to get away with deprecating it. But you can basically create new APIs that add new functionality without necessarily breaking the old one. Breaking comes at a high cost. Here's an example of something that was terrible JavaScript decision. So there was a thing called with, and basically with was dynamic scope. It basically injected dynamically into the scope whatever happened to be on person. And the thing that sucks about this is that if you're a compiler and you're reading this, you basically cannot figure out what name means here. It could be person.name, but it could also be window.name, and you cannot do anything about it. So the reason why this is okay is that in V1, you have not really done any interesting optimizations, and the scope is literally represented as a dictionary somewhere. So you're like, oh, no problem. I'll just look it up, and I'll just inject a new scope into the scope chain. Seems easy. Everything is great. But over time, you're going to get better and better optimizations, and this is like quite a disaster. So what browsers actually did is they didn't say, well, with is basically a disaster. We are just going to break all programs that use it, because there are a lot of programs that use it. They said, we can make it work, but if you use with in your program, basically your program is going to be slow. So we can make it work, but we're not going to make it fast. And that strategy is also a strategy that you can use when you have built a V1, you have added you have some stuff going on that didn't end up being the right thing for your global optimizations, but you have a lot of programs that already work. All this is to say there's ways to do trickery that allow you to maintain compatibility with V1, even though maybe you didn't get the exact details of the things you wanted to optimize right. And browsers have in fact been doing this for years. So the whole story of web browsers is web browsers, 20 years ago were, in today's terms, extremely slow, even considering that hardware was much slower. And browsers today are extremely fast. And Space Jam still works. How does Space Jam still work? There's many websites that still work. And the reason for that is that browsers feel the competitive pressure to keep up with native, and they do a lot of work to make things better, but they do not break compatibility basically under any circumstances. They try to figure out ways to either, worst case, we'll make it work, but we won't make it fast. But there's several steps between we just have to keep supporting it and we have to kill it. The cool thing about frameworks in general, so that's sort of the infrastructure. That's what a framework looks like. That's what a kernel looks like. It's what a JIT looks like. And the cool thing about frameworks is that because the whole worldview, the whole mental model of a framework is we're enumerating some actions. We're enumerating some set of things. Please read from a socket. Please call this function. Please make the DOM, this piece of the DOM, reflect this property, right? You're not saying exactly how to do it. You're saying what you want to get done. Because that's how the worldview works. As a practical matter, if you made something work in V1, it will actually work in V2. Now, you could imagine removing, completely rewriting things, but the framework worldview is all about keeping things working. The kernel worldview is all about keeping things working that were working before, optimizing the existing code as best as you can, and adding more and more declarative facilities that let you do better and better optimizations. So in Linux, an example of that would be epoll, right? So there were select. It's not like epoll is better, therefore we have killed select, which is the old story. It's you should really use epoll, and if you're using select, it's slow, but it still works. So I guess what I'm saying is a thing that kind of rankles me is about the current JavaScript ecosystem is this idea that the web is changing so fast that you can't actually build an application that lasts more than a year or two. You basically, I've heard people say over and over again, well, you have to rewrite it anyway. And I think the story of web browsers, the story of programming languages like JavaScript, the story of web browsers, operating systems, shows you that doesn't have to be true. right? You can wildly change the performance characteristics, the programming model of things without breaking existing programs. And so I really want people to think about not how do I take advantage of the latest hype, even though usually it's good to think about why it's hypey. What's the important thing? I want people to think about how do I build a program that I can still work on in 2 years or 3 years or 4 years or 5, right? I've been working on Skylight for now 3 or 4 years. We started on Ember 0.9. I want people to be able to do that. I want people to be able to think about what is the model, what is the world that we could construct that allows people to continue to build applications and code bases over time that take advantage of new features that don't stagnate, but still don't have to be written all the time. I call that stability without stagnation. And I think the way to do that is this model, the kernel model, the browser model, the framework model. So really what that means is that what's the reason why you have frameworks? The reason you have frameworks is that you have a domain where there's a ton of shared state somewhere. In the browser, it's the DOM and the network. In the operating system, it's like all of your memory, right? Where you really want to be able to build big programs with isolated units. You want isolation because that's an important way of building programs that scale, but you want to have a way to optimize duplicated work, shared work. And I think we need to think more about how to build systems like that, not just at the operating system level or at the language level, but at the framework level, right? There's no reason why once you have reached the language level, you're done with domain-specific kernels, right? So I think of Ember sort of as a domain-specific operating system for doing the specific thing that we're doing. We found a bunch of shared state that's not encapsulated by some other kernel, and we have created a kernel. And I think I want people to spend more time thinking about how to build systems that last, that allow people to build apps that last. So thank you very much.
Thank you, Yehuda. That was wonderful. And I have a quick question for you to follow up on your presentation.
Sure.
And then we'll go to an audience question here. So my question to you is there ever the case that you should actually deprecate that old functionality just because a new programmer who is embracing the framework for the first time might go down a path that is not ideal as a best programming practice? And we kind of realize later on, hey, this is not probably ideal. So let's remove it. Let's sacrifice breaking applications. Let's go ahead and break some of them because we don't want new programmers to use this functionality because it's just a bad practice. Is there
so first of all, I think it's important to differentiate between deprecate and remove. I think sometimes people say deprecate when they mean remove, and I think that's what you mean right this second. But I think the thing to realize is that we actually have a pretty good answer for that, which is basically the Douglas Crockford, the good parts idea, which is you try to construct, you make linting tools, you try to construct, you basically create a subset world that you can teach people, that you enforce via tooling, that doesn't have the bad parts in it. Maybe you stop documenting on MDN, or you put a big red warning on MDN that says don't use this anymore. But that there's a whole set of, you can start telling people in the console, why are you doing this? You're a bad person, right? But there's a whole set of things that you can try before you break things. I think people reach for the nuclear option of breaking existing apps too quickly. Maybe you have to do it if you try really hard and you sorry, nobody is actually changing. But in practice, that doesn't seem like what happens because the carrot of performance is so great.
Makes sense. Great. So there's two questions here that are related. They're both around React and Angular. So maybe we can just answer them together. So the question is, how do you see Ember progressing in the future as the community keeps fighting the React versus Angular war, and what's your predictions for React and Angular and those frameworks in the future?
So my strategy with Ember has always been to not fight the wars, and to basically focus on building effectively the Linux strategy of just keep shipping things that add more features, that give people basically add more actions that allow users to say the things that they want, try to use the information that we have to optimize things better. I think you can see that we did that last year with Glimmer. We basically took existing templates, extracted more information out of them, and made them go faster. I think the React and Angular worlds really buy into the idea that because things are changing a lot, you have to break things a lot. And I think that works to a point. I think basically the thing I was trying to say about the V1 and V2 thing is that there's sort of this ramping up point where the first period of it looks slow, But then over time, because you're building on what you already had, you get more and more mileage out of it. And I really don't mind if my competitors keep rebooting all the time, because they can reboot, and in the meantime, I'm just continuing to build on what I already have. And I would also not mind if other people took up my call to arms and tried to maintain compatibility, not for compatibility's sake, but because you can, for all the reasons I said in the talk. But I think that's the state, right?
Well said. So then next question with 33 votes from Miroslav is, what makes the difference between a good programmer and a great programmer?
I literally do not know how to answer that question, but...
Well, maybe another way to phrase this would be, what do you look for in programmers who collaborate with you?
So that is a better question, a version of the question. I want to just say in response to the first question that I think every person is sometimes a bad programmer. Like, I am sometimes a bad programmer. And I think I fight really hard against the mindset that, well, if we only hire good programmers, nobody will ever write bad code. I think bad code is the result of, it's a combination of skill level and cognitive depletion, and everyone is eventually cognitively depleted, so you eventually have bad code. So I think it's good to not think about people as monotonically on a scale of quality of programmer, but also like multiplied by their level of cognitive depletion. So that's one aspect. Another sort of related point to that is there's a lot of things that people do in programming that is actually unrelated to their level of like banging out code skills. Like API design, empathy with the user, like how you react to bug reports, like there's documentation, tons of stuff. Like Leia, Silber, who's on the Ember Core team, but is not actually a programmer, managed the entire effort to get all the deprecation notices from Ember 113 documented, including like interacting with users who were submitting pull requests, all that stuff. And she doesn't actually do any programming, right? So I think people overestimate how much the exact skill of programming is important for getting the job done. So I would say I also don't like to think of programming as being the core skill. But in terms of what I think I look for in collaborators is basically people who look two things. So one, people are always looking for like, oh, how do I improve my existing base of skills and knowledge to a bigger area? But second of all, they're more concretely people who look at problems and say, okay, there's a problem. Here are the 6 constraints that I am aware of. I can think about how to solve the problem. Oh, a user has said that doesn't satisfy the requirement. Let me ask them what is the new constraint and try to figure out how to incorporate the constraint, right? So that's a way of solving a problem, is try to say, oh, people are saying I need this feature. Why are they saying that? People, for example, people reported a long time ago, like the 6-week release cycle in Ember is too fast. That is not an actual constraint, right? The actual constraint is things like, I feel like if I don't upgrade, I'm not going to get security patches, right? So that's the real constraint. And the thing I look for in primarily in programmers is people who are able to look at problems and say, not what are the fake constraints or the things people are saying, but what are the actual core constraints that exist here? And sometimes the core constraints are like, emotionally, people cannot handle that. That's a real constraint. That might be real. But you should arrive at that being a constraint instead of letting people claim that the problem is some technical detail when in fact what they're saying is emotionally I can't handle that. Which is, again, fine. It's a real thing in the world. You have to deal with it. So I think just in general, I really bristle at working with people who, it's like the faster horse thing, right? I bristle at working with people who tell me, this is a constraint. This is a non-negotiable constraint. You have not, here is a thing that you need to do, but you have to implement it this way. That is the constraint. This is the required implementation.
Great, thank you, Yehuda. So we're just about out of time here, but before we go, I want to review the poll that we asked here, which is, do you use a front-end or back-end framework in your day-to-day job? Yehuda was very curious to find this out. And a whopping 86% of the audience does use a front-end or back-end framework.
Yes. So the reason I asked that question is because there is a claim in the world that frameworks have been a total failure and cannot manage complexity. It is like self-evident. Everybody realizes that they're a failure. Yet almost every app in the world uses them. So clearly, people should try to address their cognitive dissonance about, like, it's one thing to say it doesn't work that well, or here is a model, but the models that people postulate as alternatives do not actually exist at scale, and frameworks actually do. So the idea that frameworks fundamentally cannot build like Square is wrong. It's like an incorrect statement. And I would like people who both use frameworks every day and also are sympathetic to this position to try to resolve the cognitive dissonance.
Thank you, Yehuda. Are you available for a few private questions from our audience? Do you have a few minutes?
Absolutely, yeah.
Great. So I'm going to go ahead and paste the link to the Google Hangouts in the chat window. Yehuda, I really want to thank you for being here with us today. You've taken a stand for coding nonprofits. I know how busy you are with your development schedule, and I just really want to acknowledge you for that. Very, very enlightening conversation. So thank you today, Yehuda.
Thank you.
All right, we'll be right back, guys.